Hello everyone. So today we will be having an example on pile foundation. In this particular example, we are going to calculate the ultimate point load on the pile or the toe capacity, or we call it also end bearing capacity. So we are given a precast concrete pile having a length of 12 meters. Say this is our pile. It has a length of 12 meters. Which is driven into a homogeneous sand. So the soil throughout is sand, which means that our cohesion or drain cohesion is 0. The pile is square, having a cross section of 305 millimeter by 305 millimeter. So we can say this is 0.305 meters by 0.305 meters. A dry unit weight is given to be 16.8 kilonewton per cubic meter. And the average angle of friction for this sand is equal to 35 degrees. So with these parameters, we are asked to solve for the ultimate load here, Q sub P. Point load, or the end bearing, or we can call it also tip capacity, using the Mayer-Hobbs method. So this is based on the Mayer-Hobbs method for for piles in sand. The Mayer-Hobbs method for sand can be found in the book, having a formula equal to the area of the pile tip multiplied by the bearing capacity, or it can also be equal to A sub P Q prime, which is the overburden pressure multiplied by N sub Q. Okay, this formula is also derived from the general bearing capacity equation, um, but considering zero cohesion, or since this is for sand, the derived formula is this one. This can be found on page 660 of the book by Das and Sivakugan, equation 18.13. So let us write, this is equation 18.13 for your reference. Okay, so this formula should be less than, or the value of the point load using this Mayer-Hobbs should be less than a limiting value of A sub P Q times L, or Q by L, Q sub L rather, wherein Q sub L is equal to 50 and sub Q asterisk tangent angle of friction, the drained angle of friction. Okay, so let's first solve for Q sub P, which is equivalent to Q prime by N sub Q. N sub Q is the bearing capacity factor based on the figure here. So this is the Meyerhoff's bearing capacity factor, which is a relationship between the soil angle of friction and the N sub Q here. Okay, this side. So it's white, I cannot here. Okay, since we have the angle of friction, solving for N sub Q for an angle of friction of 35 degrees. This is 35 degrees. Let me emphasize. This is 35. Okay, here. And let's get the intersection. So from here, from their intersection, we can, okay, it's not very clear, so let me consider another color. Okay. So from this figure, we can say that our N sub Q for an angle of friction of 35 degrees, N sub Q is approximately about 120. Okay, then we have Q. Say Q is the overburden pressure, which is equal to unit weight multiplied by the length. So since this is a homogeneous soil, we have what we call the limiting value of L, which is the actual embedment length, or L sub B, which is also equal to our L. This is for the homogeneous soil. But if our soil is not homogeneous, we have to calculate the maximum value of embedment. All right, so Q prime is equal to the unit weight, which is 16.8. This is in kilonewton per cubic meter multiplied by the length of 12 meters. So our Q is equivalent to 201.6 kilonewton per square meter. So we already have Q and N sub Q. A sub P is simply equal to the area, the cross-sectional area of our square pile, which is 0.305 by 0.305. This is in meter square rather, or this is equivalent to 0.930 meter square. So since we have all the parameters, we can now calculate for Q sub P, capital Q sub P, which is the load in kilonewton. So we have area of the tip. Okay, that's actually the area of the tip here. We consider the area of the tip here, which is the same as the cross-sectional area on top. So this is 0.930. This is in meter square multiplied by Q, 201.6 kilonewton per square meter multiplied by the bearing capacity factor of 120. So obviously, the unit becomes kilonewton, and calculating, we can get a value equivalent to 2,250 kilonewton. So 2,250 is the ultimate capacity. at the tip of the pile or at the end of the pile. But again, this should be less than a limiting value of, we have A sub P multiplied by Q sub L, or this one. So we can just write A sub P multiplied by 50 N sub Q tangent of our angle of friction. So let us check if is it less than? Is it less than or equal? A sub P is 0.930. We have 50 here. We have N sub Q is still 120 and tangent of 35 degrees. So if you calculate this one, the value is 390.7. This is in kilonewton. So obviously, this is the calculated point bearing capacity here is greater than and not less than the limiting value. So this is not true. Therefore, we cannot adopt the 2,250. The ultimate point bearing load that can be applied to our pile is only 390.7 kilonewton. So that is the answer.